Okay, so I welcome you all. And in our last class, what we did is we talked about bosonic operators. And finally, we obtained the commutation relation between the creation and annihilation operators. And if we sketch out that thing, it was like, suppose I have a state, a vacuum state 0, right? I have a vacuum state and I act an operator on it, say a zeta I dagger. Now what is a zeta I dagger? It's a creation operator. What will it do? It will enclose a particle in the quantum state. So this vacuum state will turn into a state with one particle in it. Now, if I again use an operator A zeta I, a creation operator, what will happen? You will have a state with two number of particles. And this can go as much as particles you are interested in. And you can think in the reverse direction also. So if you have two particles in your quantum state, and if you use an annihilation operator, you will reach here, right?
Yes.
And if you again use the annihilation operator, A zeta cap, you will use to this state, the vacuum state. And if you again use an annihilation operator here, the result will be 0, because you don't have any particle in the vacuum state. Clear? So this is how the bosonic creation and annihilation operators work. And what is beautiful about bosonic is that there is no change in the sign of the wave function when you interchange the particles. And this is the first important implication of bosonic systems. The next important implication is you can have as many as particles in your quantum state. So now we will move into the fermionic operators. So before going into the idea of fermionic operators, we again will start with the Fock space, and we will be using these creation and annihilation operators, but we have to keep in mind the two fundamental postulates. The very first postulate is, since you are dealing with the fermionic system, if you interchange the position of your particles, the sign of the entire wave function is going to change. Right? This is the first important implication of fermionic systems. The next important, yeah? If you interchange the position of the two particles, the sign of the overall wave function will change, right? And the second important implication is you cannot have a quantum. Yes? The sign will change. So if you started with a positive eigenstate, if your Fock space is filled with the positive state, it will turn into a negative state, right? By simply exchanging the particles. The next important implication is you cannot have two particles in the same quantum state. Now what does that mean? That means if somehow you encounter a situation where you have two particles in the same quantum state, your wave function, your whole system will vanish. It will lead us to 0. So these are the two important starting points to talk about the fermionic operators. Now, So we'll be discussing fermionic operators. Fermionic operators. Okay. Now I will start with my basis vector. Say I will take a zeta I as my basis vector belonging to some v. And what I have a state, say ui, uj, uk, and so on and so forth. Now, the point is that I have to introduce the operators, and I would like to use these operators on my force space and see what are the important implications, what are the important outcomes. So I will start with a creation operator. A creation operator. What kind of markers you have brought? I cannot see it. Okay. So the creation operator, I will choose C zeta I dagger. Okay? Assuming that this C zeta I dagger is a creation operator in fermionic systems. And I can keep a cap on it. And the annihilation operator, the annihilation operator, C zeta I cap. So here, C zeta I dagger is my creation operator, and C zeta I cap is the annihilation. Is this clear? Okay. Now I choose C zeta I. See, I'm using I dagger. I choose it on uj, uk, and so on and so forth. This is my quantum state. uj, uk, it can be anything, kl, un, it can go on and on. Now what am I doing? I'm using a creation operator on this state. So what will be the outcome? Yes, the outcome will be ui, uj, uk, and so on and so forth. You have created a system of operators, right? ui, C zeta I dagger acting on this state will add ui to this state, right?
Yes, sir.
Okay, fine. Now, if I choose another state, say I choose uk, uj, and so on and so forth, and I use C zeta I creation operator, what will happen? So you will have a state with ui, uk, come on, uk and uj and so on and so forth. Is this clear? Now what is the difference between the two? In the first case you have ui, j and k. In the second case you have ui, then you have uk and you have uj. But I want to make it resembling with my previous state. So what should I do for that? Come on. What should I do? Yes?
Annihilation.
Don't have to do anything like that. I would like to bring this J here and K there. But what should I keep in mind? I have to introduce the negative sign. So here I will have minus Ui, Uj and Uk. So you can see, if you correlate these two systems, they are not equal. They can be equal only if you interchange the position of Ui and Uj, leading us to have a negative sign to this point. So here you see, you have to take care of the order of your states. If you change the order, you have to keep in mind that you have to introduce the negative sign. And it's as equally as true. If you make two exchanges in your quantum state, what will be the result? The result will be the same thing. Because for the first exchange you will get negative, for another exchange you will get another negative, and that will take you back to your original quantum state. Is this clear? Okay. So, on the similar configurations, if I have Ci cap acting on Uj, Uk, Ul, let me start with Ui. What will happen here? This Ui will be annihilated by this operator because I am acting I. So I will not act on K and J. Yes. It will act on I. So what will it do? It will annihilate Ui. So what will be the result? The result will be Uj, Uk and Ul. So what you have? You have JKL. Right? Now if you interchange the order between K and L, you have to introduce the negative sign. If you change from K to J, you have to introduce the negative sign. Is this clear? So here we can see how an annihilation operator acts on your quantum state. Right? Yes. So what it does, it annihilates the particle in your system. Now see. Now suppose I write here CK. See, what is important here is the order. I'm using an annihilation operator CK. Now why is K? K is the third term. Right? Now this is not going to act on it like this. You have three persons. You want to kill the third one. He has to come in front of the shooter. God forbid. So the same thing is here. What you have to interchange it. So you will act this CK. So this is UI. This will become UK and UJ and so on and so forth. It will introduce the negative sign, the first negative sign. But it is not coming in front of our operator. Yes. So again, you will have an exchange. So it will become CK. So this will be UK, UI and UJ and so on and so forth. Now it will act on your UK. So what will be the result? The result will be UI and UJ and so on. Is this clear? Yes. So this is how the annihilation operator acts on your quantum system. Because here the order is of vital importance. If you fail to keep the order of the system, the results that you obtain will not be consistent. The results will be wrong. Is this clear to you? Okay. Now, when we talk about the bosons, they have commutation relations. And when we talk about the fermions, they have anti-commutation relations. Now, why they have anti-commutation relations? Because of those two fundamental postulates that I talked about. Right? Pauli's exclusion principle and the vanishing of the quantum state if you have the two particles in the same quantum state. Okay. So now, what I choose for commutators, you have the square brackets. But for anti-commutators, you have curly brackets. This is A and B operators. And if you anti-commute between A and B, this is always equal to A, B plus B, A. Right? Now, I will choose my operators. What are they? Ci dagger and Cj dagger. And I want to obtain the anti-commutation relation between Ci dagger and Cj dagger. Both of them are creation operators. Right? So, what will be their anti-commutation? That will be Ci dagger, Cj dagger plus Cj dagger, Ci dagger. Right? Yes. So now, the first thing that I would like to calculate is Ci dagger and Cj dagger. Right? So what I have Ci dagger and Cj dagger acting on UK, UL, and so on and so forth. Okay? So Ci dagger, Cj dagger. What will Cj dagger do on this state? It will give me Uj. Clear? So what will I get for the first operator that will act on this quantum state? What will you obtain? Come on. What will happen? You will have Ci dagger there, but Cj will act and it will lead us to what? Uj, UK, and so on and so forth. Right? Fine? Okay? Now Ci dagger, what will it lead? It will lead it to Ui, Uj, and UK, and so on and so forth. This is Ci dagger, Cj dagger. Right? Now, what will I do? I will use Cj dagger and Ci dagger. Right? Am I doing it right? Here you have introduced J and you have introduced I. Now, come on. Now you have the same quantum state. What I will do? I will use Cj dagger and Ci dagger. Okay, you will act it on the same state. What is that? UK, UL, and so on and so forth. Right? Now, what will this I do? It will add a UI to our fork space. So what you will have? You will have Cj dagger, and here you will have UI, then you will have UK, and you will have UL, and so on and so forth. Now, this will create another state, another set of particles. What will be that? That will be Uj, Ui, UK, and so on and so forth. Is this clear? But I want this to look like this. So what should I do? I will make it Ui, Uj. I want to make it like that. So for that, I have to use exclusion principle. So exchanging the position of the two particles will lead us to have a negative sign. So what you will get here, minus the same thing. Ui, Uj, and so on and so forth. Are you getting my point? Now, what we had to obtain? We had to obtain the anti-commutation. And the anti-commutation was given by what? It was given by Ci dagger, Cj dagger plus Cj dagger, Ci dagger. Now look at the two equations. You have to add them, but you have a negative sign, and you are with the same quantum states. They will cancel. Will they cancel? Yes. And what you will get? You will get 0. So what is happening? The two fermions anti-commute with each other. So that means what you have? You have Ci dagger, Cj dagger. Their anti-commutation leads to 0. Is this clear? This is clear. Now, if this is clear, so this leads us to what? It leads us to the anti-commutation between Ci dagger and Cj dagger. Now, the next task for us is to obtain the anti-commutation between two anti-annihilation operators. Right? That's our next thing that we would like to obtain from him. So how we can do that? Come on. Yes? Come on. Yeah. You can do it. Come on, you can do it. But you have the anti-commutation between Ci cap and Cj cap. And this will also take our result equal to 0. So you'll do it, okay? Right? Okay. And then you will have the third relation. What will be the result of the third relation? That will be Ci and Cj dagger. And this will come out to be delta Ij. And you will obtain this result also. Okay? Yes. Now, what we have is, we would like to summarize these two things. The two things that we have, the first thing is, I have a Fock space N, and I use an creation operator A zeta I dagger. It leads my Fock space to Fn plus 1 in case of bosons, right? Right? Yes. And if you go reverse and you apply A zeta I annihilation, your Fn plus 1 will lead us to Fn. Right? So there is addition of the particles in the Fock space in bosonic system. And you can have infinite number of particles that you can add in your bosonic system. But that's not the case with fermionic system. I want to exploit this point, what I said. Let us exploit this point. Because here you don't have any problem in bosonic system. You exchange the particles, doesn't matter. You add the particles, doesn't matter. Right? Now let's try to analyze the fermionic system with the addition of a particle. What does that mean? Suppose I have AI dagger, and it is acting on a system, say UI, UJ, UK, and so on and so forth. Come on, tell me what will be the result of this creation operator on this quantum state? Yes? Come on. And there is another, say, AI dagger, I will call it a J dagger, UI, UJ, UK, and so on. Yes? You already have a UI number of particles in this quantum state. Now, you want to add another particle to the same quantum state. That's a violation of Pauli's exclusion principle. So what will be the result of this? It will be zero. The whole hierarchical system based on the configuration of electrons will collapse theoretically if you are adding a creation operator, if you are adding a particle which is already existing in your system in the same quantum state. So the same thing is happening here, because you have a UJ state, right? And you cannot add another particle in the same quantum state. This is how fermionic Fock space, the fermionic system, differs with the bosonic system. Is this clear? Okay. Any queries? Any questions? Yes?
सर एक मिनट ये गाना बहुत सुने तो fermionic का वहाँ पर ऐड होता है, यहाँ पर नहीं होता है ऐड। मतलब कि ये जो अभी आपने रखा ना इसमें ऐड नहीं हुआ, मतलब कि वहाँ पर हमें जीरो मिला रिजल्ट।
Yeah, it all collapses.
तो ये fermionic के वहाँ पर ऐड होता है और वहाँ पर ये नहीं, वहाँ पर जीरो नहीं बनेगा। मतलब कि हम वहाँ पर ऐड भी कर सकते हैं तो ये।
Yes, you can add any number of particles in bosonic system. Yes.
bosonic में नहीं होता है।
In bosonic, you can add any number of particles
यहाँ पर तो जीरो मिला हमें भी।
because it's a fermionic system. You cannot have two particles in the same quantum state.
सर यहाँ पर हमने A से रिप्रेजेंट किया है, हमने C से रिप्रेजेंट किया है।
Yeah.
तो C और A से मैं कंफ्यूज हूँ।
No, you don't have, these are just.
हमें किसी भी नाम लिख सकते
Yeah,
हैं।
the choice goes with the book, the choice goes with you. You can have your own choice.
B से
To start with the basis vector state. Okay.
हम B से भी रिप्रेजेंट कर
You can also represent it by B. There's nothing wrong with that. Okay? That's not the problem. Now see, come on. If I write down something like this, UI, UJ, UK, and then I have CI dagger. Come on, don't talk. Then I have UJ, UK, and so on and so forth. Come on, how will you solve it? Give me the result. Come on, what will be the value? say we have to presume that we are considering all basic properties, the orthogonality of the basis vectors, right? All of these things have to be considered here, whatever we are doing. So what will be the result of this matrix element? It will be 1. It will be 1. Why? Because this will create a UI state here. So what you will have UI, UJ and UK. This will create UI and UJ and UK. Now since they are orthogonal to each other, so the result of this will be equal to 1. Now, I want to take its adjoint. I want to take its adjoint. I want to take the dagger of this thing. Come on, what you'll do with it? Say, come on, this will brainstorm you. Because you can use this technique also to obtain the commutation relations. Come on, yes? How do you say that? Now see, what will happen? When you take the adjoint, what happens? What happens? The bra will become cat, your cat will become the bra. So what will happen here? You will have UJ will come here. And you will have UK is here. And CI, I have to take its adjoint. So this is CI dagger. I have to take its dagger. Okay? Then I will act on what? Then I will act on UI. Here it has to be I now. This is UI, UJ, and so on and so forth. Right? So what will happen? CI dagger's dagger. The adjoint of CI dagger will give us CI. It will give us annihilation of it. Would it do that?
Yes.
So this is UJ, UK, and so on and so forth. So this will give us Ci cap along. So it will take the particle from your quantum state. So what is it here? It is Ui, Uj, and so on and so forth. So what will happen? This Ui will, but what you have? You have a star of everything, right? So what you will get here? You will get Uj, Uk. This will kill this Ui. It will kill it. So what will remain? Uj, Uk, star. So what is the value of this? 1. So it will be 1 star. But the star of 1 is always 1. So the answer to this problem is equal to 1. Got it?
Yes.
Got it? You have to practice. You have to work out these things. And you must be strong enough to manipulate the particles in these quantum systems. Either in a bosonic system and in the fermionic system. So with this, we would like to stop here. Okay?